Hello, my name is Craig Schultz, and I'm presenting flat panel haptics, embedded electroosmotic pumps for scalable shape displays. This work was done during my postdoc with Chris Harrison and the Future Interfaces group at Carnegie Mellon. Reprogrammable shape-shifting computer interfaces have captured our collective imagination for decades. Here's a clip from the original X-Men movie showing a general-purpose 2.5D shape display. It's made up of hundreds or even thousands of programmable pixels which spring to life and animate our hero's master plan. This vision has not just been limited to the movies, however, as there's also a long history of researchers building various shape-shifting and fingertip display interfaces. On the surface, these approaches are great. Even with only tens of actuators, you can start to see a glimmer of an ultimate haptic display, or, as one researcher called it, the holy grail of haptics. But there's one major problem with the previous approaches. They simply don't scale. If you want to build high-resolution, general-purpose displays, these technologies need to be miniaturized so that they can scale up. This is where our work comes in. Our main contribution is to provide a vision and demonstration of miniaturizable, scalable shape displays. At the outset, we asked ourselves if current shape displays are sort of like a CRT monitor, which are effective but overall expensive, complicated, and bulky, could we envision and build a flat panel haptic shape display? Something that's more like a modern LCD, cheaper, simpler, and slimmer. What I came up with is a new approach and what I call a flat panel haptic display. Here's a video of one of our systems shown in real time. Rows of bumps are emerging from the surface under computer control. Note that the whole stack up here is under 5 millimeters thick. I fabricated this device from scratch after quite a long process of iteration. It's got a stretchy elastomer surface that's actuated by an array of individually controlled pumps. What's causing the shape change here is pressurized fluid inflating and deflating each output pixel. The hydraulic system is entirely self-contained, powered and controlled only by an electrical cable. It's lightweight, in this case under 40 grams. Enabling this small of a form factor is a new actuation technique I call embedded electroosmotic pumps, or EEOPs. Here's a schematic of how these work. Each pump pulls fluid from a common reservoir and pressurizes the output elastomer layer. On the right, you're seeing this process happen repeatedly with a prototype. Note that the pump active layer is only about 1/4 of a millimeter thick. It's actually embedded in the device itself. I'm going to put an arrow on it just to point out how small it really is. If you take a cross-section of just the pump, this is what it looks like under a microscope. I can apply an input voltage across the two electrodes, and almost like magic, fluid flows in the system. Going back to the idea of coming up with a flat panel haptic display, it should be noted that this configuration is in fact very similar to the principle of liquid crystal displays, or LCDs. The embedded liquid crystal layer either blocks or allows light from a backlight to pass through, depending on the applied voltage. And this type of approach of embedding the active element directly into a surface is how you get the thinness and large numbers of elements you need for really large pixel densities. So how does this work? Please read our paper for more information, but here's a quick primer. These pumps use an electrokinetic effect known as electroosmotic flow. In fluid at rest, charged species of ions are uniformly distributed, as seen here. But when you bring a solid into the liquid, a non-uniform surface charge builds up at the interface. This is called the electrical double layer. So now you have an accumulated charge density in the fluid, just outside the solid surface, and is free to move in the liquid. So how do you get charge to move? Well, you put an electric field. So if I take some external electrodes and apply a voltage on them, the charges will begin to slide. The mobile charges then viscously couple to the rest of the fluid, and what was originally as just a surface flow becomes a bulk flow. Voila, you have direct voltage to flow transduction. I'll briefly mention the pump's main construction components, as this is another key aspect of this approach. I used all off-the-shelf, easily attainable materials: silicone, glass fiber, PET, common sheet adhesives, and in the middle there's a PCB. This PCB is critical to the miniaturization process as the modern precision of commodity PCB lithography and CNC drilling enables complex electrode patterning and practical system routing at almost negligible cost. All of these materials were ordered or processed in-house and then assembled in layers. The entire stack-up was designed with the idea of scalability in mind. Whether you're building one actuator, 50, or 100, the process is really not all that different. I characterized the pump's performance with a series of physical tests. I built pumps of various sizes ranging from 2 mm to 10 mm in diameter, as seen here. These pumps in two conditions, a block pressure condition and an open flow condition. This is similar to the stall torque and no load velocity characterization of an electric motor. Here's an example plot of open flow. You can see how flow is directly proportional to the applied electric field. Note that the float also goes both positive and negative, as this effect is sensitive to voltage polarity and is completely bidirectional. The results from tests across all different pump sizes for a range of different voltages. You can see that both flow and pressure are relatively linear and increase with voltage. Flow is proportional to pump area, while pressure is independent of pump area, as predicted by theory. If I plot one of our EEOPs here in red against a wide variety of other micropumps, you can see that we have achieved one of the smallest pump volumes and highest volume normalized flow rates ever shown in the literature. This means that these pumps are incredibly small and can move large amounts of fluid for their size. Pump displacement by pushing up against a piston connected to a displacement measurement device. You can see the displacement scales with pump diameter and rapidly increases before reaching a maximum. Using the same piston, I applied different weight loads and measured the force capability. An average output layer can push up against at least 100 grams of force, about the typical interaction force coming from a user. I also tested some of these devices directly with users. Using 4 mm and 8 mm diameter actuators, I applied pulsing waveforms at 3 different timescales, 1/4 Hz, 1 Hz, and 10 Hz, and users rested their finger on top of each device and reported whether they could feel or not feel a certain stimuli. Results from this absolute detection threshold experiment showed that all the users could feel the stimuli at peak voltages below 200 volts. A few example applications to showcase the potential of flat panel haptic displays. General purpose shape displays can take on a variety of surface patterns, like these textures, numbers, icons, or even UI elements or emojis. Media control panel, which can offer dynamic tactile affordances and more complex shape geometries. So I was able to take an off-the-shelf flexible OLED, the kind that are in today's holding smartphones, and actuate it from below. What results is now a deformable visual display with icons like this setting button, which can animate to show a notification, button which slowly breathes in and out until I click it to dismiss it. This technique can also give us back the tactile keyboards that we lost when we made the transition to touchscreens. Here's a keyboard popping up under my finger. I'm also showing it with the screen off here for better clarity. In this work, I introduced my vision for flat panel haptic shape displays. I built and characterized device stackups based on embedded electroosmotic pumps, or EEOPs. These devices are under 5 mm in thickness with a 1/4 mm thick active layer, yet they can still generate plus or minus 50 kilopascals of pressure, and this can be used to inflate hydraulic actuators in under 1 second. These initial prototypes were detectable by users with under 200 volts applied. And finally, I showcased 3 different sample applications: a general purpose display, a pop-up interface, and a flexible OLED touchscreen. Please see our paper for more details.